Are almost.
This meeting is being recorded.
I suppose it's time to get started. Well, good afternoon, ladies and gentlemen, to all of you who have kindly decided to join us for what promises to be a very interesting conversation with a real hands-on expert on matters that have to do with America, space exploration, technology, budgets, and more. And our guest today, Mr. Jonathan Gal-Edd, he really knows, because he's been there, I would say, as we say, around the block many, many, many times, and he's a veteran of NASA. Before we get into it, let me just say quickly, my name is Paolo von Schirach. I serve as president of the Global Policy Institute, a research institution here in Washington, D.C. We're just, for whatever it's worth, a couple of blocks from the White House in downtown D.C. I also am privileged to serve as chair of the Political Science and International Relations Department at Bay Atlantic University. The two institutions, Bay Atlantic University and GPI, the Global Policy Institute, work together, and we're very happy to be able to put this event together as others prior to this and coming up, and you will find out very soon. So without further ado, let's get right into it. We are going to talk today about the National Aerospace Administration. It's kind of the nerve center, the management center of the US space program. Well, we'll find out if it's brain dead or not, probably not. Because otherwise, if it were brain dead, I would not have been mesmerized just as a member of the general public when I saw this news and I watched this, kind of how can I say, renditions of the opening up of the Webb Telescope. And when I saw this enormous piece of highly sophisticated machinery with a mirror, which I think, you correct me if I'm wrong, is the size of a tennis court, and how it was deployed into space and sequenced in terms of its progressive opening, and so that it could become fully functional, and that this was, kind of managed here from Earth, and that it happened flawlessly in space, I say, oh boy, we can really do something here. And it's amazing because this new telescope will open up new vistas in terms of our better understanding of the universe and seeing objects way, way, way far that we cannot even comprehend. And prior to that, I suppose as many others, I was equally mesmerized when I saw the sequencing of the launching and the flawless landing on Mars, the planet Mars, of a vehicle, a whole thing. And it was parachuted onto the Martian atmosphere, such as it is, and flawlessly landed, and then accompanied by a little drone and all that. And I thought that the names given to these two items, persistence and ingenuity, well, maybe that, in a sense, I hope these two nicknames given by kids, by the way, after a national kind of contest, in a sense, summarize where we are. Persistence, being, stick to it, and ingenuity, open to new ideas, trying something different and whatnot. Anyway, I am a layperson. I understand nothing about engineering and about technology and about space matters. Maybe I can hardly recognize, a star. Maybe I know where the moon is, but that's about as far as I go. So this is why here today we have our good friend who is going to tell us, hopefully in ways that most of us can understand, what this is all about. What is NASA? How did it get started? What is its mission? And lights and shadows. Not everything went flawlessly. Not all programs, were, wonderfully executed. But without further ado, let me give the floor to our guest. By the way, you have his bio, rather long and distinguished, in the flyer, so I will not repeat his many professional and other accomplishments, but I would like him to get started and see what we can learn. Thank you.
Excellent, thank you. So I'm Jonathan, thank you, Paulo, for the very warm introduction. And as Paulo said, in Christmas, we launched the James Webb Telescope, and it's an end of an engineering era. Now it's a beginning of a science era. But as an engineer, we live the engineering projects and we move to the next projects. So I will share with you two major projects that I worked on. One is the James Webb Telescope and the other the International Space Station. And I'll give you some insight from behind the scenes and a little bit what you see as the big picture. I'll try to put in a big picture. And without further ado, I'll jump into the presentation. So give me a second because I need to go to a presentation mode. Am I sharing?
Yes.
Okay, so let me hide and let me go to, okay.
Yeah.
So I think Paul already did this portion, so I touched on it. I'm going to discuss two major projects. So I wanted to start with kind of setting a little bit of the background. My story, or the stories of my presentations, begin in the mid-'80s with the space station. So I want to start with a little bit of background how NASA operates. So our budget, as Paulo said, actually he said it's 23 billion a year, but it hasn't moved up. It's linked to the inflation. And since the early 17s, our budget has been frozen. So with this budget, we need to spread between science missions and what we call manned or human missions. And also, you need to spread the money between operational missions and new development missions. So it's a big juggling priority act. As NASA is a major institution, there's a lot of states that want to get a chunk of this 20-some billion dollars. And the way the money is distributed, it's either we have 14 centers which are distributed all around the United States, and we have also subcontractors or contractors that build many of the stuff for us. And again, they're also distributed all over the United States. So because these are congressional programs that we want to get congressional support, you can't do it all in one location. But the focus of, out of the 14 centers and all that, I want to focus on 5 NASA centers locations, which some of you've heard on, and this is sorted alphabetically. So the Goddard Space Flight Center is right here around Washington, D.C. It's in Greenbelt, Maryland, and the focus or the charter is for Earth observing mission, satellites that look back on Earth. So it's many of the NOAA satellites, USGS, US Geological Survey that map, and telescopes. And the telescopes was the Barbara Malkovsky's contribution, and I'll talk a little bit more about them. The second category or the second group is and Paulo talked about it, is all the missions that go to Mars, and I won't discuss more other than mention them here. They're over in Pasadena, a suburb of Los Angeles. It's the Jet Propulsion Lab, which is adjacent to Caltech. They do Mars missions, rovers, and the big thing that they're going to work in the next 10 years, which is worthy of a presentation by itself, is called Mars Return Sample. All the work in Mars today, we build laboratories with robots and rovers that go and collect, and they actually sample where they are. The Mars sample return will put capsules, put them on Mars, and then the next satellite is going to come collect them and bring them back to Earth, and will actually bring portions of Mars back to Earth. So that's the Mars sample return mission that they're working on, and I don't have the dates, but by the end, by 2030, they want to do, and again, that's an international collaboration with ESA. The next center is down in Houston, Texas, Johnson Space Center. Everything that has to do with astronauts training, mission control, all the manned programs go from Houston. And many of you saw the movie Apollo 13. Houston, I have a problem, so that's that. And the asterisk there means I worked several years there, and I'll touch on that. Kennedy Space Center is where, in order to get to space, that's the gateway from the United States for most of our flights. We needed a location that there's no humans next to it. It's the most eastern location in the United States. Most of our satellites, they go straight to the equator. So if you go towards the equator, we go straight over water, and then God forbid, if something happens to the rocket, we can just let the rocket explode, but not over human areas. So that's why Cape Canaveral over in Florida is a strategic location. They also do the payload processing there. We send the payloads, which is the satellites themselves. The rockets get brought down to Kennedy Space Center, and they combine the two together, and that's what we have a launch. And the last center I'm going to talk about is Marshall Space Center. That's in Huntsville, Alabama. They're responsible to build rockets. So that kind of gives you the idea where these centers are and what they do functionally. So the history, I mean, I'm going to touch more on manned missions because that's where a lot of the infrastructure and all the money goes. So in the 60s, there was the Cold War, and the Russians managed twice to surprise the United States. One was in the late 50s when they first sent a dog to space, and then Yuri Gagarin was the first human in space. So Kennedy wanted to win the race to space, so he said, by the end of the decade, you guys are going to get me to the moon. And what the Americans did, they brought over from Germany the Nazis that built the rockets in World War II against the Americans. They brought them to Huntsville, Alabama, built a small little village, gave them money, and they were responsible to build the rocket that later on was the successful, it's the Saturn rocket. And then in 1969, the Americans landed on the moon, and indeed we met the charter that was given by President Kennedy. And up until today, the landing on the moon is considered one of NASA's biggest accomplishments. Now, we had two more missions, two more Apollo missions. We went to the moon twice more, and then they decided to stop the program because there was no more. People weren't as excited as they were after the first two missions. So the way, unfortunately or fortunately, the way the Americans work on manned missions is there's a stop, and then they plan the next generation of manned missions. So the next generation of missions was Skylab. You can go to the Smithsonian and Air and Space Museum, actually see it. I won't touch more about it. It was a low-key project. It happened in 1973, and between 1970 and 1981, there was very little astronaut activity. And they began working on this new generation thing, which is called the Space Shuttle. And in 1981, we had the first Space Shuttle. And the last Space Shuttle was in 2011, and I'll discuss that a little bit. So now I'm setting the background. So 1981 was the first Space Shuttle, and all the programs, the major flagship programs in NASA, the space station and the Hubble Space Telescope, and some other programs were built to use astronauts and to sit. If you look at the picture of the Hubble, it opens in the back. That's the bay, and everything size-wise and deployment came out of the Hubble. So out of the shuttle. So the shuttle went up to space. Inside there was a satellite, there was an arm, a robotic arm. They lifted it up and then they deployed or took the pieces up. So everything was geared size-wise, mass-wise to fit inside the shuttle. And everything, things were working okay until 1986. 1986, there was the Challenger accident. So what happened then, NASA decided they felt that there wasn't enough oversight of NASA over contractors, so they decided to build, for the space station program, to build a new office, an integration office in Washington, D.C., actually in Reston, Virginia. And I was, at the time, I worked for Boeing as a contractor on something totally different, but there were so many openings, and it was a big contract that everybody that in this area that worked for a defense contractor and all that, we kind of went there because there were a lot of jobs and our companies needed, to fill positions and all that stuff. So I ended up working for NASA because of the Challenger accident. And, sometimes you need to be the right person was very exciting for me because I came from Israel in '84, and this was kind of to work on such a big project working for NASA was very exciting. The next step with the shuttle program was the Hubble telescope. They actually were supposed to launch in '86, but because of the accident, they kind of had to postpone it, and they launched in 1990. Now, what I want you to see on the bottom is that each, and I'll touch on that a little later, is the human flights. They require a lot of infrastructure because you have to build the rockets, you have to build all the facilities to test the rockets, et cetera, communication. So there's a lot of infrastructure investment that goes behind the scenes when these programs, that's why these programs take 20, 30 years and beyond. So you have my resume that Paolo shared with you, but I want to show you kind of my hands-on items that I touched and are now in space, starting from the left quadrant on the left corner to the top. So that's the space station. Then you have 3 missions that have Goddard next to them. They have either letters or numbers, and that means that these are missions that are continuous looking at Earth, and they need to be replenished every 5, 7, or 10 years, because the product that we need on Earth, it's just the satellites have a lifetime of 10 years maximum, and we want to, so like the NOAA satellites are the ones that when you see TV, all the weather satellites, those are NASA builds them, we give them to NOAA, and then we have a satellite in the east and the west, and those are the 2 satellites that you see on all the TV stations here, and et cetera, et cetera. So those are 3 examples. So I was fortunate enough to work on the series that was relevant between 2011 and 2022. As a matter of fact, the Ghost T is going to launch in a few weeks from Cape Canaveral, and I'm going to go see the launch. Then on the left corner on the bottom here, I'm going to point with the cursor, is a very exciting mission that I worked on, and it's if I get invited, it's worth its own presentation. That's a sample return mission called OSIRIS-REx, was launched in 2016. It landed on the asteroid in 2020. It did the sample, and maybe 2021, collected the sample. Now 2 more years, it's going to go back and come back and land in Utah, and then we're actually going to bring another piece of space back to Earth. Then the James Webb Telescope that launched in Christmas, and I'll discuss more about it. So now you have a feeling of my overall background and what I did in Houston, what I did over in Goddard. So the next portion of the presentation will talk about the International Space Station. So the first part of the space station was over in Reston, Virginia, between 1986 and 1992. I mentioned that NASA wanted to do, or the government wanted to do integration from Washington, D.C. with oversight. Because it was a multi-location, multi-NASA system, we had to build an infrastructure to combine all of the NASA centers so they can communicate, exchange information. So I was fortunate to work on a system that had to integrate all of those NASA centers with a local area network. Now, nowadays, you buy a PC and it comes with wireless and an Ethernet card and all that stuff. But that was not the situation in the mid-'80s. The mid-'80s, we had IBM mainframes, we had mini computers that did office automation. The PC had a floppy disk, and how to integrate all 3 was not doable. So I was lucky enough to work on one of the first local area network systems, and we deployed at all of the NASA centers, and I'll touch on that in a minute, but that kind of helped me meet a lot of people and helped me with my career later on. So between 86 and 92, it was called Space Station Freedom. They worked on it. The budget was about $1 billion a year. And in 1990, people saw that it wasn't producing the amount of productivity that we wanted. So what one does when the project doesn't work, they rename it. They reorganize it, they forget the old name, they change all the people, and they start from scratch. So in 1993, they came up with a new program that essentially does the same functionality called the International Space Station, managed in Houston. And the changes were we moved it away from Washington. We made an integrator. Instead of the government, we let Boeing integrate it. There's four pieces of it, so we let Boeing do the integration. We added an international partner, so they won't cancel the program. It's always good to have an international partner. And I was offered a job because I had good contacts, because I built the local area network as a civil servant, has come down to Houston and help us with, whatever we need down there. And then later on, I had to leave for family reasons, but leave Houston. But I left very close to the first flight over the International Space Station. So the first model in 1993, we gave the contract to Boeing. Actually, it was 94, but 93 we wrote all the specifications. 5 years, Boeing began doing the integration, and 1998 was the first flight model and we completed, or NASA completed, the construction over a period of 13 years of the International Space Station. So this is just a picture that I got the Employee of the Year award in 1990 when I worked at NASA headquarters. I went down with my family to see a shuttle launch. It was a big honor. It was a very cool thing to do. Just had to show off a little bit. So that's that. So I want to touch a little bit on the space station, which the idea there is a marvel in engineering, not by having one piece, but construction in space. It demonstrates how you can work in space. It took 37 shuttle flights and over 75 Russian flights to build this thing, so over 100 flights. And then since 2011, we began using some commercial, the Dragon with SpaceX, with Elon Musk, and Northrop Grumman over from Antares, they launched it from Wallops, to do supply, to bring up supplies. Half of the cargo that we send back is junk, human junk, because of all the, people need to eat and et cetera. They create dirt and all that stuff. So half of the payloads that go up and down is just for the humans that we have to do. Half of the payload is new experiments, et cetera, et cetera. So this gives you the sheer size of this program. But then there's a problem, because if you try to do 100 things in space, sooner or later, one will have an accident. It's very, statistically to have no fault, which brings me to the next picture. So what you're seeing here is the picture of the leftovers of the Space Shuttle Columbia, that in February 1st, 2003, there was the accident when the Columbia returned and burnt. And this is a horrifying picture, which actually, I saw this in person, but this was, when people saw this reconstruction, they decided in 2003, we need to close the shuttle program. It's a question of time. Let's finish building the space station. Let's do a few more things with the shuttle, but that was the end of the shuttle program. We cannot continue having this risk of once every 100 flights to go through this. So I'm sorry that I'm sharing this kind of image with you, but that's the reality of what happened. So in 2011, we completed the construction of a space station, and that was the last shuttle flight. And this is where there's another gap in the capability of the United States to send an astronaut. From 2011 up until 2020. United States did not have a capability to send an astronaut to space. Our astronauts had to go to Baikonur, which belongs to Russia, next to and send the astronauts there. And they used to go up and down with the Soyuz to come to the space station. So there was like 9 years of us not having capability, and there was a lot of pressure for us to have capability. And Elon Musk, which is very innovative, jumped in, and in 2020, right after the corona started, I think it was the May of 2020, he sent astronauts up in a SpaceX. And I showed you the picture before. So rather than put the payload on the same capsule, he put a capsule with 4 astronauts, and they went to the space station. And starting in 2020, we started with going back and forth to space station, and then there's a few flights since. We are still using the Russian, but there's transition, there's a date that the United States is going to decide we're going only American, we're going to stop with the Russians. So it took us from 2011 up to 2020 to have US capabilities. In parallel, United States is working on a program to go to Mars, human to Mars, through a way station and habitat on the moon. They call the program Artemis. We're starting now what we call the design and concept phase, with the goal to get to the moon with a habitat in 2025. And as I touched on earlier, there's a lot of infrastructure that needs to be in place. So we need to build a new rocket because the astronauts are heavy. So we need to build, going to the moon, you need a much stronger and bigger rocket than going to the space station, because the moon is 200,000 kilometers out, while the space station is 300 kilometers. So you need a much bigger rocket. So we're working on that. You need a capsule, which can put astronauts inside, and it's for a longer journey, not like these small capsules that they sit inside. And that's only to get to the moon. And then when we get to the moon, we actually want to go and build a habitat on the moon and not send supplies up and down. We want to be independent on the moon. So we decided to go to the south pole of the moon, because if you look at the moon, the middle of the moon, the center is all desert, but the poles have ice on them. So they feel that we can harvest the ice, that there's oxygen, so there's water and ice. So we want to go to the south pole. If you go to the south pole of the moon, you create a challenge with communication, because the poles of the moon, you only see them for 14 days out of the month. The moon has a dark side and the side we can see and the not dark side. So when the Apollo programs went, they landed in the center of the moon. They had continuous view of the Earth, continuous coverage with communications. But if we go to the South Pole, either we have to go to sorties that are only 14 days long, or we need to build a relay satellite behind the South Pole that will relay communication back to Earth. So that's one challenge. And then if we want to go to Mars, we need supply stations where we can refill oxygen on the way, refuel. We want to fix satellites in space, change their batteries, et cetera, et cetera. I mean, we need like the equivalent of gas stations and service stations and all that. So in order to get to Mars, we need to build a very robust infrastructure. So that is kind of what they're thinking about. And the first step is doing it around the moon with the habitat. I'm just giving you the pieces. You go look back at the budget. The budget's 23 billion a year. We need 100 billion. So with 3 or 4 or 5 billion a year, it'll take many, many years to build this infrastructure.
Yeah.
And that's kind of what I have to say about space station and the human flight. Are there any questions? Because I'm going to switch.
Yeah, let me thank you so much for this great narrative, Jonathan. Let me ask you a pedestrian layman's question. All this stuff looks great, right? But for people who just are not scientists, and they ask, so why are we doing all this? In other words,
well, because we don't.
What is the point of all this?
There's something pioneering American. I can't answer you because I'm a civil servant. I have to give you a lot of science people ask the same question. Ask. However, Americans feel they've always been pioneering and going to Mars. It's like the same way that we conquered the West with Lewis and Clark. So yeah. Going to Mars with an astronaut has been a dream of several presidents, and that's kind of their vision. Going to a planet and living there. It's a vision it's an American vision that captures the imagination of people. We believe. Some of us believe that will capture the imagination. So I hope I answered you in the most.
Well, here's the story. I don't know exactly how to put it. I think it was President Kennedy, right, who said
yes.
Space is going to be the new frontier. Wasn't he the one who said that?
He was. Yes, he was the first. Yes,
if I'm not mistaken. But the question is. The frontier that you alluded to, colonizing and populating the west of the United States, that was about human settlements. That was about people moving west and going to, creating
Right.
cities and farms and living there. Now, it's a bit of a jump to say, oh, we're going to do the same thing because we're going to put the cities and colonies on the moon and then on Mars and this and that. It's really a long shot. So again, I for one say this is fantastic. This ingenuity, this incredible prowess of our science, it's really, wonderful. But then I think the problem, which is, if I summarize it as, looking at public policy, if this is so important, if this captures the imagination of the population, why such a small budget, right? We spend a lot more money on golf courses, probably grass, I don't know, in the United States. Then I'm just joking. Maybe it's not true. But I'm saying we're spending a lot of money on things which are clearly not, they're sort of frivolous and not particularly
Right.
So why do you think that your agency cannot command more interest in Washington when it comes to the yearly federal budget? And you cannot say, hey, we're doing something really great. Give us not 23 billion, but 40 billion, 50 billion, whatever is necessary.
First, I'll answer your question in two parts. Why it's important. And now what I'm telling you is I don't want you to stop the recording, but this is my opinion. And sure. You're asking me very direct questions, and I'm a very direct guy. So one of the things that's behind the scenes, or not so much behind the scenes, that the United States, people in my community, and I'm talking about high-level people that are strategic people, feel that we're losing to China. That China has become, it's not Russia anymore. China has become very dominant in space, and China's gonna, if you look at the number of engineers that China's producing per year and math graduates, etc., they have a very strong infrastructure. And a lot of people are concerned that if the United States doesn't overall as a government invest in these type of programs, because even if we don't get to Mars, it increases engineering, increases technology, it makes you think, it gives you some something to think about. And they feel that there's a China now. So that's unofficially what I'm telling you. And this I heard from high-level people at NASA and some ex-astronauts that actually stepped on the moon. So that's that part. About the budget, that's part of the challenge that we all have as government employees, is that we have two parties that are very different in their priorities. We have a Democratic Party and we have a Republican Party. The Republicans like to spend money on more things like space and NASA and defense. The Democrats are more social. So to give you specifics, and I don't want to touch Biden now because there's Corona and Trump, but Bush tried in 2007 when he was the president, said he started, we called it at the time, constellation, go back to Mars. As a matter of fact, his father visioned it back in 1980 whenever his father was the father Bush was the president. But then Obama came in 2008 and said, this is not a priority. Everything that we want is Obamacare, social, etc. You NASA stay within budget. So I'm just giving you a political between two presidents that happened before, and I don't want to talk about politics today, but that was you could see overnight the shift in priorities between Obama and, as a matter of fact, and I know I'm on a tangent, it's not part of the presentation, but it's inside information. Obama said, why are we wasting our time going to Mars? Let's go to asteroid. And guess who worked on an asteroid? I moved from working on Mars, or not on Mars, working on space station or the next frontier to Mars to go work on an asteroid because Obama said asteroid. And we went 4 missions to an asteroid, one after the other, when Obama was the president. So there is when the president wants something, the agencies salute and we do what the politicians tell us. I hope I answered you without going to jail.
Listen, no, thank you for that and for your candor. And I know it's, being there from the inside, but
Well,
But so,
what I'm telling you is facts. You can say I can't guess what's happening today, but that's
yes, but
okay.
so let's stick to the to the
Okay.
value proposition as you were saying, and then we'll get back to your presentation. But
Okay.
you were saying that there is a competition in space, right? There is a you mentioned China, you mentioned great investments, etc.
Yes.
It is
yes.
no secret. This goes back to the very beginning, as you mentioned, the competition between the United States and the then Soviet Union. That there is also, there are all these great programs, manned exploration, going to the moon, etc. But there is also technology that can make a country dominant in space,
Correct.
which could have clearly military implication or ripple effects down the line. That's not what NASA does. I understand there's not a military program, but clearly maintaining an edge and a leading edge on the technology, on the space technologies of the future is really important in a global competitive environment. Did I get you right? Which is where
yes. So we want to stay dominant. United States wants to stay dominant in space as a national priority. Whatever, how you define dominant in space is a little more tricky, but I believe by having a man in space, that's somehow people will interpret it. And that's the way we should leave it at this point, Paolo. I think I answered what you asked with as much
Thank you. Let's move on.
insight as I can without tiptoeing. Okay. So the next portion, so now we're going to roll forward, talk about James Webb. And again, I'll give you a little bit of background, what happened before. So prior to James Webb, we had a telescope called the Space Hubble. And as I mentioned earlier, everything was tailored to should they say shuttle and not shuttle? I don't know. I need to fix this. And the whole idea with the shuttle was twofold. One, it would fit and be deployed from the shuttle. And number two, we will have servicing missions that will fix. Fortunate for us, this mission was planned as serviceable because the first shuttle launch in 1990, I don't know if any of you remember, was a failure because the optics of the shuttle did not work correctly. The first images of the Hubble were very blurred. The reason was that the test equipment on Earth was not calibrated correctly, so we fixed the optics of the telescope to be deformed to meet the test equipment, and then we went to space, everything was blurred. So from 1990 till 1993, we waited until an astronaut came up and he actually put another lens on top of the shuttle, put like a contact lens on top, and then suddenly the Hubble, with a shuttle mission, the servicing mission number one is what fixed the Hubble. So it took an extra mission and another few more years before the Hubble began producing what it needed. And then the whole idea, every 3 years, as you see on the left there, we sent servicing missions, we changed one instrument, we changed the computer. So rather than build something for many years, the way we fixed it, we sent an astronaut up and fixed it and all that stuff. And indeed, every time it gave more functionality, extended the life. They fixed the solar panels because meteors and there were holes in them, et cetera, et cetera. Now, there's two sides to every mission. There's the engineering side, which I work on, which is the building, and then there's the science producing side of it. And the Space Telescope is very strategically important for Maryland because all the big astronomers of the world sit in a building called STSCI, Space Telescope Institute in Baltimore, behind the campus of Johns Hopkins University. And Barbara Malkovsky arranged it that way because she's from Baltimore, so she wanted,
So this is a late senator from Maryland, right?
Yes, the late senator from Maryland. So the smart people that do all the processing of the data and all the science people are sitting in Baltimore. So it's not only the engineering, it gives a lot of work. And Barbara Malkovsky likes gray cells jobs for Maryland. She doesn't want hamburger flippers. That's the way she spoke. That's what she said. That was a charter to be elected. And she actually brought some good jobs to Baltimore. Now, as the space, what happens with the Hubble telescope, it's still producing great science, but one, it's eroding because we can't fix it anymore with service missions. And number two, the technology on Earth to build bigger Earth telescopes has been that it almost meets what we can do from space. So in Chile now, there's a 35-meter telescope on Earth that almost can do what the Hubble can do. So the next generation, so in 1996, the first phase of every mission is what we call a concept phase, and I joined in 98, is to begin working on a concept. What will the next generation space telescope look like? With the goal by 2010 to replace the Hubble Space Telescope. So we started the concept in 98 with the goal by 2010 to have the next generation is to provide more data for the people in Baltimore to generate more science, et cetera, et cetera. So that's kind of the why the push for Webb. And here I'm giving you side by side what the concept kind of came up with, why the Webb was, and we called it at the time, was called the Next Generation Space Telescope. So the Hubble telescope's, the size of the mirror is 2.4 meters. The Webb is 6.5 side to side, so it's 9 times bigger square meters. And the collecting area of the telescope is very, very important. It's like a camera. The bigger your lens, the more light you collect, the more capability you can collecting more light. So that's one thing. So the size of the mirror was much bigger. The second thing was the Hubble was monolithic. It's glass, and it was deformed, and it has problems when you go around the Earth. It warms up and it gets cold, so it gets deformed, and you need to keep the temperature very stable. So the James Webb is built on software. It has 18 segments, and I'll show a little bit more about this later. And they're all controlled individually, and with software, we take the image and collect it together. So that's a different type of technology, but we had to do that because of the size. To build a monolithic 26 square meter is impossible. There isn't material to do that. The Hubble is near Earth, so in a LEO stands for low Earth orbiting. It's 300 kilometers from Earth. So it has two of the problems that I already mentioned. One is that it heats and cools because when it looks at the sun, it's very hot, and then when it goes behind Earth, it cools down. And the other is that because Earth radiates heat and light, the images that you can see with Hubble are, they call it background limited to the heat and the light of Earth. When you, in camera and photography, when you look out of your window, you can only see images that you need to be in the dark to look out at images that are lighter than you. So that's kind of basic photography. Cooling, you want the detectors inside the instruments, inside the camera. There's the detector, what we call pixels, or what you're used to in all your stuff. So the cooler they are, the better science they produce, because that's the way the technology is. So in the Hubble, we have a cryo cooler, which is just another machine that creates noise and all that. But we wanted to, it causes vibrations and all that. So on James Webb, we wanted to do the cooling passive, and I'll talk about that. And last but not least, because when L1, it can't be serviceable. So the next generation needs to work first time out of the box. We can't fix anything. Shuttle was serviceable. So those were the 5 spec charter things that became as the next generation, concept study. And the concept, this is what we came up with, just to give you show you the size of people. So now you see 400 people standing. This is the size of James Webb compared to people, that you'll see how big of an object in space this is compared to humans. And behind you have the building that my bosses work out. This is the NASA headquarters in Greenbelt. So I gave you the specification, what we wanted it to do now, kind of a little more down to technology things. So the capability of imaging is you need to see a head of a penny from Los Angeles to Florida. That is the distance. If I hold a penny in Florida and I look from Los Angeles, I can read the head of a penny. That is the optic capability of the combination of the telescope and the detectors. I touched on it. We need to do that. We need a very big collecting area, which we decided will be 26 square meters. The detectors need to be very cold. 26 Kelvin is extremely cold. 0 Kelvin is as low as you can get, and this is very, very cold temperature. We touched on passive cooling, and there's a thing called a sun shield, and I'll talk about this a little more. And there's 4 instruments. So we collect with the telescope, but there's 4 instruments that actually take the light from the telescope, and based on frequency, they look at different ranges of the spectrum and give different images. We have a mid-infrared, and we have a near-infrared, and we have a spectrometer. So each instrument, they're very big and very complicated. 2 of the instruments are international contribution. There's a Canadian instrument and a European instrument. And you need all of this to work together in an integrated way. You need the optics to be very stable, because you don't want the images to be blurred and change on you. You need to keep it thermal, between from the sun, so thermally that it will be stable. And also you have a lot of machinery in the warm side. On the spacecraft side, there's computers and all that. So you need all the heat from those, you need to keep it away from the cold detectors and from the telescope side. And you need this thing to be very, very stable in space, because you don't want to shake. Like when you take pictures, you don't want to shake. And I showed you earlier the size of this thing, and it has such a big sail to it. It's like a sailboat. So to keep all this, you want to keep it stable, cold, and thermally in order to provide good images. So that's the challenge of, it's not only the optical system, it's not only the thermal system, it's only the spacecraft. This is what we call integrated modeling. You need all these pieces to work together to provide a good image. So that's why this is a very challenging engineering exercise to do all this.
All right.
Yes, so that's kind of the challenge. So also we were lucky as far as the public affair goes. In 2007, our chief scientist was John Maver was selected to get a Nobel Prize. And it's very cool when somebody walked down the hall. You wake up in the morning, because the announcement was in Europe at 2 in the morning, and you come to work, and John, my next door neighbor, suddenly got the Nobel Prize, and he's the first NASA employee to win the prize. And of course, then there's the question: if he gets the $1 million, which each Nobel Prize winner gets, will he get it or will NASA get it? Those are the kind of things that really, when you get a Nobel Prize. But anyhow, it was very cool with John, and it caused a big excitement, because we got visibility that way, it's worthwhile doing the science, etc. So back to the telescope, we have 2 major portions that need to work. So the one item is the telescope itself, and I touched on it. So and I'll put the cursor, I hope I can get it, if you can see it. So there's 18 segments. Each segment is about 1.3 meters. And then it's 6 meters from side to side. And so we have 18 independent segments, each controlled by actuators, by little springs that you can move each segment up and down to make it kind of the right size and the right position to collect the light. The material is beryllium and not glass, because beryllium is much more stable. It doesn't change. Its thermal stability is from hot to cold. It's an exotic material, so it's much more difficult to work. It's powder. You need special tools for it. It's not as easy as glass to work with, but in order to have this kind of high tech, we had to deal with beryllium. I talked about the actuators, and there's a whole process, which I think we're doing now, and they're sharing pictures on the internet. It's called wavefront control, where we take every one of these segments and we align them. We look at, there's a star that we know its behavior and what it looks like, and we're doing all the calibration of each of the segments against the star. That's called wavefront control. We align each segment individually, and then with software, we combine all the images, and so in a few months, once we're done with that, we can begin collecting science. So that's the telescope side of the telescope. I actually saw, this is 2019. I was actually out there in Los Angeles before we finished the integration, and you see the sun shield on the bottom. So this is the telescope, and it's actually folded because when you go up to space, you couldn't keep it all open. So the telescope was folded in thirds. 1/3 is here, you have the center, and when you go up to space, all the pieces come together, and you see here, the bottom is the sun shield. This is the real telescope in its factory in Redondo Beach, California in 2019. The next thing that needs to make this mission work is this sun shield. I mentioned the importance of things being cold. So the sun comes from this side, and we have 5 layers. And the goal is to go down from, with passive cooling, just using this aluminum material, which you see the size of each, and we have 5 layers of it. We get the temperature down from 383 Kelvin down to 36 Kelvin passively. So the first 2 layers bring down the temperature the most, and then et cetera, until we get down to the temperature that we need. And then again, this is in the lab that we tested over and off of Grumman. These are pictures in the lab. You see the United States flag and all the equipment around, so you know this is not in space. Now, the sun shield is very, very big, and the telescope is very, very big. And now the challenge is to go up to space.
Sorry, Jonathan, could I ask you to summarize as
Sure.
much as you can so that we have a little time for quite a few questions from the audience, because we are approaching, unfortunately, the end of the time allocated to us.
Well, that's fine. So all I'm saying, it's very challenging to get those 2 pieces together, and you have to put them in the capsule and deploy them. So and there's a movie here that you guys can later on look, and I'm almost towards the end. So all I wanted to do is just a few takeaways, Polo, with your.
Sure, please.
So these projects take a long time. They take a lot of people. So and I think I touched both on James Webb and on Space Station. They take reorganization. We didn't get it up by 2010 with James Webb. It took us an extra 10 years. It takes time and patience. And you need continuous congressional and science support. If you lose your support, the funding disappears and these projects disappears, and we have examples of those kind of projects. And last but not least, and especially in the case of James Webb, failure wasn't an option. So we needed a very rigorous test program. It took us 5 years to test the sun shield in gravity environment, because deploying in space, there's 0 gravity the size. So we couldn't open 5 layers with gravity, would have ripped the material and all that. So we needed to come with creative ideas how to test it. So we over tested it, and we had to do a lot of things here on Earth to make sure that it works in space. So that's kind of, I wanted to share that there was a lot of smarts put into the test program. We over tested it here to make sure that it's going to work in space. And I think that's kind of my takeaway, and I'm done to stay on schedule.
All right, wonderful. Thank you again, Jonathan. This is really extremely, illuminating for us, the lay people. And we have a lot of interest in our students and others who are kind enough to follow us in this webinar. Of course, a question that was asked is a little bit something that we had touched upon earlier, and that is about what's so important. I guess you already answered that question. Why is it that we should even bother to explore space when there are so many other things, probably more urgent priorities in terms of social needs and economic needs?
Well, with social needs, that's in your election. You can vote for another party, and then you spend the money
in a different way. Yeah, fair enough. And then we had another question about cooperation. But again, that was also, I think, embedded in your part of your.
Yeah, I can answer it. Okay.
So in other words, somebody asking, are we cooperating with other countries? Well, the answer, I think, is yes. The Webb Telescope is with the European Space Agency and with the Canadian, but maybe you can elaborate further in terms of other joint ventures or partnerships or what have you between NASA and other countries.
It's tricky. Yes, we want to partner with other countries. However, you're very dependent on other budgets of other people's countries. It's not as simple as one thinks. So the consensus in the United States on programs is that the rockets, the infrastructure, we're not going to partner on. We want our own rocket. We want our own certain things. We can partner on things like instruments, but not on the spacecraft. So I don't know if I'm answering the question. So it's not the critical parts of the mission. It's value add items, but so for instance, on James Webb, the telescope and the NIRCam instrument are American. If the Europeans won't show up, we would have one. Well, it's a very important instrument, but it's not the instruments that the America needed for what the American mission was. I don't know if I answered your question and all that stuff. Yes, we would like international partnership because it gives us more science, more capability, etc. And I mentioned on space station, without the Russians, we would have been lost, but it's.
Can I ask you a question? I mean, SpaceX, which some people know about, everybody kind of heard of Elon Musk, but of course, right, in the minds of most people, he's associated with electric vehicles, with Tesla. Many know, and that he also has this very, very important venture called SpaceX. To me, as a layperson, he seems to have succeeded greatly in cost effectiveness. In other words, his company seems to be able to do a lot more with less in terms of funding, in terms of reusable components of rockets and what have you. Do you think that that is the future? In other words, that we will be able to commoditize, in a sense, space programs by making them more ordinary, simple stuff, relatively speaking, and more affordable so you can have more of them. Is SpaceX telling us something about the future of the US space program?
So the answer is yes and no, and I'm happy you asked this, because life is about risk rewards. It's all about statistics. There's no free lunch. So Elon Musk is a statistics guy. He says it's all about economics. I can't guarantee you 100%. You take parts. So when NASA used parts before Elon Musk, we used the highest type parts. We radiation tested them. We used to throw out from 100 parts, we picked the 4 best ones, throw out 80 pieces that didn't meet the criteria. Elon Musk goes to Radio Shack, uses the same computer. Everything's fine, but then you go to space, you have a solar flare. So I don't know if you read last week, Elon Musk had 40 satellites that went into limbo. There was a solar flare, and his whole mission went kaput. Now, if I would have sent out this James Webb Telescope and it would have gone kaput like Elon Musk, I would have made the Washington Post front page and all that stuff. So there's a risk reward that I can't always quantity. I think that to answer the question, I think there's somewhere in between NASA's conservatism and Elon Musk where the world will end up in the end, but he's a little too, that's my personal opinion. There's, a happy media, and you need to know when to take risks. But for me, when I work on a project, each project is individual, and failure is not an option. I cannot. You follow my success is on my project. I can say, but I did great last time. If James Webb wouldn't have worked, would have been a disaster to my center. You follow what I don't know if I'm explaining.
Sure. Oh, you make sense. All right.
So I think I answered you as specific. And
yeah.
He screwed up big time last week, if you haven't heard about it.
So somebody else is asking us about Artemis, about delays or other other issues, and then also about other players in this sphere. Jeff Bezos, what's he all about? This whole idea of space tourism or what have you. So for Artemis, which is a serious thing, and Bezos, which is space tourism. Okay.
Well, I think that to get to the moon, getting to space station, getting to Leo is relatively, I don't want to say simple, but that's getting to the moon. We need a rocket the size of the Saturn. We need the German Nazi ingenuity, and Musk is the only guy that I think has the infrastructure to get there. All these people that are going what we call Leo. I'm not trying to pick on it and all that kind of stuff. So I can't say much about Artemis. I mean, because I don't know enough about it, but the building the rocket is a key component. There's two competing rockets. There's a NASA-built rocket, which is, they change the acronym every year. It's the NLS, the new launch system, or the HLS, the heavy launch system, which we're trying to build under the government, and Musk has his own version. And competition is wonderful. If one of the two work, NASA's not stupid. NASA's going to pick the one that works, and that's where we are now. Neither one has demonstrated. I think I answered you. We don't. I think there's a demonstration of the rocket next year, but the first component is we need a bigger rocket. The rockets that take us to space station are not going to get us to the moon.
I think we're getting really to the end of our time, but there's another question about space trash, which I think you probably are very familiar with, right? All this old things, abandoned, broken down, dead pieces. How serious a matter is this? The more of us, and that's just Americans, is the Russians, the Chinese, the Indians, everybody's throwing stuff into space, and then it's junk. And
it is a very big problem, and it
can hurt. It can collide with other live systems and destroy them or disable them. Correct?
Right. Yes. So we have the Air Force, actually, not NASA. They track as many objects as they can, and we call this collision avoidance. Before I do a maneuver, I go to the database of the Air Force. It's a 24 hours warning, because these objects don't move as fast as you can, and I have enough propellant to avoid them. So when I go every day, I look at the database and I try to do collision avoidance. So if I know there's a particle that's coming my way, I can do it. The only issue is that the database collects certain size of particles. If the particles are smaller, I don't see them. They don't cause continuous damage to me and all that stuff. So the other thing that you have to do is you have to build smarter satellites with backup systems, with redundancy, with solar panels that are bigger. So if I lose half of the solar panel, I still have enough power to survive and all that. So there's the cost of surviving. The more if the environment is hard on you, the more expensive the mission is to meet its goal, 10-year goal, 5-year goals, etc. So it is a problem. It's like humans. The way we say the space is, go look at the ocean. You remember when the ocean was clean? Now you have plastic bags that kill turtles and trash, and so the same is in space. Sooner or later, it's going to look like the ocean. I don't know. That's the.
But can you envisage a system in the future? Maybe not. We can't do it now, where you collect literally this space garbage and you remove it.
I guess they'll have to do it sooner or later, because it'll be like the ocean. The moment
too much stuff. But it will be expensive. It will be complicated, because it will be a lot of it, and it's not like.
I know. As I said, it's the day that we have a lot of stations and a lot of satellites in low orbit. I gave you examples, cameras, etc., communication satellites, and those are functions that you need on Earth. And if we lose all that capability in space, we'll have to do something to clean the debris. It's just, how life is.
Yeah. Well, I think we're really getting to the end of it. May I ask you just this? Is Webb now operational? Is it beginning to, or not yet?
No, so we are now in the calibration period.
Okay.
So where it is, it's all the system have been deployed. So all the mechanisms have been deployed. It's all where it needs to be in space. All the magnets and all that are so the sun shield is open, the telescope is open. Now they're doing the 18 hexagons one by one. And there was a selfie. If you look on, it's taking selfie of one. They have a camera that makes sure that each one of these hexagons with its magnets, the springs in the back, the actuators is all deploying. Once they do all these 18, they're going to collect an image, and then in a month or so, they're not looking at the star that's science, but they're looking at the star for calibration. Once they finish calibrating, they'll begin looking. I think they promised June that they'll begin science.
So basically, when Webb is operational, we will have the landscape view of the universe. We will be able to see way into the depth of the galaxies and the and this
6
incredible
billion,
universe.
6 billion years back.
Well, that is something. That gives me as
give or take a billion years. 6 billion.
All right. Well, I'll take a few billion. Anyway, Jonathan, thank you so much, and thanks to
thank you for the
all
opportunity.
our kind audience that has been with us and the questions. We appreciate your knowledge and expertise and sharing with us.
Sure.
Again, this is something that most of us honestly don't know enough. And it's important. It's about science. It's about knowledge. It's about, as you say, the human aspiration to learn, but it's also about technology, engineering, about harnessing different players, industry, the private sector, government funding, universities, great people, great minds, and indeed international cooperation and partnership. Let's hope that this progresses, and I wish you a double budget for next year.
Hey, everybody wants a double budget. And I appreciate, I'm getting a lot of compliments and the attendance. I saw there was a lot of, so I appreciate you bringing smart people together. You asked me some tough questions there, Paolo. That wasn't fair.
All right.
I put my hands in it, I was like,
okay.
You're killing me.
Okay. Listen, thank you very much. And thanks to everybody. And thanks to my good friend and colleague, Denise, who, as always, has flawlessly put this together and arranged for our speaker and for all of us to share this.
Thank you.
This platform. And on behalf of the Global Policy Institute and Bay Atlantic University, thank you, Jonathan. Thank you, Denise. Thank you all for being here.